Okay, here is an example, a fun one, that we can use the rigid body kinematics to solve a wheelie problem. Assume we have this bike here. The total mass is 100 kilogram and the center of mass location is somehow described relative to the back wheel. And the question is, how fast should the biker accelerate to maintain this wheelie position? Before solving this, it's a good idea to have the intuition what we are dealing with. Assuming that the bike is stationary, is not moving, it is practically impossible to maintain this posture because you would just fall back down. You would not be able to maintain this. The only way you can maintain it is to accelerate fast enough. Essentially, the back wheel pushes you from underneath fast enough with enough force that creates this backward movement that resists the moment of gravity. So that's why you need acceleration, because you need force. You need a lot of force on the ground. And our goal is to find acceleration, but we should know that it is related to forces. So it is a kinematic problem. And the best idea is use free body diagram and correlate that with the knowns of the problem, see where it can take us. So for the free body diagram, I'm going to draw the entire bike here and bike all together. And this is the contact point with the ground. I know at the center of mass, the total mass of the system is acting. Let's call it W. And I know the location of it relative to the wheel. So let's actually at the same time list all our knowns. Let's call this x of g and this one y of g, some known geometrical relation. I know x of g is 1 meter, this quantity is y of g is 1 meter. I know the total mass is 100 kilogram. All of this related to this force that we have already draw. This is mg. What other forces I have? I have only one contact point with the ground, and that contact point must keep the bike from falling into the ground. So I have this normal force. And through our intuition, we established that there needs to be a big enough force on the tire, essentially the traction of the tire, that is pushing the tire forward at that contact point. And well, I didn't say it ignore all the other resistance like aerodynamic drag and so on, which is actually interesting. If you have seen any of these drag racing, super drag racing cars, sometimes they go fast enough and the aerodynamic drag is obviously not negligible there, and sometimes the front wheel lifts up a little. That causes a massive drag force and the car basically flips instantly, with sometimes flies off. So we don't do that here. We ignore aerodynamic drag. I think that is all the forces. And do we have any other information? Well, there are information that are kind of given implicitly, but you should know them. The problem says, how fast should the biker accelerate to maintain wheelie position? So that wording implies that the bike doesn't tilt further up or further down. So in other words, the bike always goes on the same straight line, and I know a y, let's call it a, yeah, let's say y is fine. A y is 0. I also know through the same wording the acceleration of the bike, the angular acceleration, is also 0. And what you need to find is essentially this ax, the acceleration in the x direction. So that is all you can have, I think. Is there anything else? Speed is not given. You are being asked to solve the problem at a single instant, so there is no transition. I think that's all. At least right now I can't think of anything else that is given to me. Okay. Now for the solution. When you are dealing with rigid body equations, well, always you can write sum of forces in vector form equals mass times acceleration. This is always true. Noting that this acceleration is acceleration of center of mass. And this F is all the external forces. Well, actually, let's write it down, so see what happens. Because I need to find AX. And forces and accelerations have this quantity, so let's do that, see where it takes us. So forces along X, I have this F, traction force that is unknown, equals MAX, and equation along Y, I have N minus mg equals MAY, that I figured is 0. So good, at least that is helpful. You know, N is mg, sure, good. But the top equation is not useful on its own. I want to find AX, but I do not know F either. If I know either of them, I can find the other. But this equation on its own is not useful for me. So the only things remains is look at the rotational equation. And for rotational equation, you have choices. You can write rotation equals about center of mass. You can always, for any situation, do this. Sum of moment about G is I about G times alpha. Note that I was not given, but because alpha is 0, we actually don't need it. So this is equals 0. And sum of moments about G is, if this is your positive rotation, if this is X, this is Y, and that is your positive rotation. In 2D, you can write, so I'm writing equations about this center of mass point G. The F times YG, the height of that, it is in my positive direction, minus N times xg equals 0. And good, now I have another equation. I can substitute N as mg, and let me continue. Here I have fyg minus N is mg, xg equals 0. So from here, noting that the bike doesn't accelerate, I can calculate F. F is mg xg divided by yg. And finally substitute everything back in my first equation. I have mg xg over yg equals max. Masses cancel out. So actually I didn't even need the mass. Did I? No. So ax is xg over yg g. So a ratio of your locations of center of mass, its height and its position, as that factors g. So if xg is 0, you're perfectly vertical. You don't need to accelerate. In fact, you shouldn't accelerate. If you accelerate, you fall back. And if y is 0, you're perfectly flat on the ground. Doesn't matter how fast you accelerate, you can never flip up. So that is one way you can solve it. There is potentially another way. You're always welcome to kind of think that way too. That this rotational equation that I wrote, it is always valid, but sometimes it becomes a little clunky, specifically in this case too, because when we start the problem, neither n or f are known. The only known force is gravity. But I can note that the moments of those two forces are 0 about the contact point because both of them pass through that contact point. So alternatively, maybe I can write moments about, let's call this point O. Not O, I don't like O. Let's call this point C for contact. Moment about this C is only minus mg, your force, times xg. And this one, I know it is related to acceleration, but because the equations are not about center of mass, I need to account essentially the kinetic moment of acceleration of center of mass. So I still have ig times alpha, but I have to account for those two other terms. So x g may minus yg max. Let me double check. Yes. All right, I think that's good. So now this is easier because now I bypass the unknown information about n and f. And in one equation, I'm relating all the accelerations together. I note that this is 0 and that one is 0. And the only two terms that remain is this one and that one. And one of them is the unknown I'm looking for. The rest are known. So in one go, I can solve the problem. The minus signs cancel out. I have, and the m's cancel out. That's nice. Okay. So I have gxg equals yg ax, or ax is the same solution, xg over yg times g. So a fraction of gravitational acceleration. So as you can see, it is possible to simplify the solution by being a bit clever and look at the setting of the problem, choosing the right set of equations. This is one of the features, not features. the things you have in rigid body kinematics, because you have a choice. It is good in the sense that you may find a way to simplify the solution. It is bad because now you have choices. If you don't have choice, you don't have to think too much. You follow the rules. But anyways, so this is a good example about how kinetics of rigid bodies can work. So I leave this here and I will see you later.